Hello everyone, I'm Shai Zhu from National Taiwan University. Today, I would like to present Motion Ring, creating illusory tactile motion around the head using 360-degree vibrotactile headbands. Haptic feedback enhances virtual experiences. Let's take a look at some commercial haptic devices. For example, there are game controllers like Xbox, PS5, and Nintendo Switch. There are also wearable devices like TactSuit from bHaptics. We can see that vibration motors are common in commercial haptic devices. However, these devices provide only static vibrations. This kind of feedback is of single point and non-moving. This limits them from creating suitable haptic feedback for game events that include the sensation of movement. For example, objects passing by the avatar, or the rapid movement relative to the environment. This is why we came to apparent tactile motion. Apparent tactile motion is an illusion that allows users to perceive a single but moving actuator when vibrotactile stimuli are placed nearby and are actuated with overlapped time series. Here we present Motion Ring, a vibrotactile headband that creates the sensation of motion around the human head through apparent tactile motion. The system works as follows. When certain game events happen, they are mapped to feedback patterns. Motion Ring then performs these feedback patterns. The Arduino board controls the motor drivers, which then actuates the array of vibration actuators in the headband. Now we have our device system ready. We would like to investigate the control space of apparent tactile motion on the head. Assume that there are two adjacent vibration motors. One vibrates first, then the other. From the temporal aspect, we have the duration of the two vibrations. Also, we have their onset interval. Here we define parameter as interstimulus onset interval, or ISOI in abbreviation. To perform the apparent tactile motion, we let an array of vibration motors vibrate in sequence. When the ISOI is too short, the user perceives one single vibration burst, which lacks the sense of motion. When the ISOI is too long, the user perceives discrete vibrations. Only when the ISOI falls in a specific interval, the user can perceive a single moving vibration. Therefore, we would like to answer the following research question. What are the upper and lower thresholds of ISOI to present smooth tactile motion on the head? We conducted a user study to understand how the thresholds are affected by the angular spacing of actuators, head regions, vibration durations, and vibration intensities. For the angular spacing of the actuators, we implemented our prototype with three different versions, with 45 degree, 30 degree, and 22.5 degree angular spacing, respectively. In our pilot study, users reported that with the 45 degree design, they only perceive discrete vibrations, so we only leave the 30 degree and the 22.5 degree design for the formal study. For each prototype design, we recruited 24 participants to join the user study. Combinations of head regions, vibration durations, and vibration intensities are fully counterbalanced. For each combination, we first experiment on the lower threshold of the ISOI, then the upper one. We follow the study procedure mentioned in Tactile Brush. The initial ISOI value is set as 0 millisecond. In every iteration, we ask the participant if they can feel a single vibration burst. If the answer is yes, we increase the ISOI value. Otherwise, we decrease it. The trial ends after the ISOI value reverses 6 times. Then we record the average of the last 4 reversals. The upper threshold is quite the same, except that the initial ISOI value is set as 300 milliseconds, and that we ask if the participant can feel discrete actuators. We hypothesized that all 4 factors affect both the lower and the upper ISOI thresholds, including the angular spacing of actuators, the head regions, the vibration durations, and the vibration intensities. We then apply 4-way ANOVA to test our hypotheses. The result shows that the angular spacing of the actuators, the vibration durations, and the vibration intensities significantly affect both the lower and the upper ISOI thresholds, but the head regions do not. Moreover, the interaction between the angular spacing of the actuators and the vibration intensities is also a significant factor. These plots show the relationship between the ISOI thresholds and the 3 single variable factors. we can see that the ISI thresholds increase as vibration duration or the angular spacing increases. As the vibration intensity increases, the ISI thresholds decrease. After knowing the control space of apparent tactile motion on the head, we want to further evaluate the user experience of motion ring. We selected 2 game events that contain motion, teleportation and objects flying by. For teleportation, we designed a VR treasure hunting game with scenes in Half-Life Alyx. We instructed the participants to teleport around to search for items. As they teleport, motion ring vibrates according to the direction and distance of their movement. For example, if they teleport straight forward, the 2 vibration motors located at the middle of the forehead vibrate first, followed by the others, performing a symmetric tactile motion. For objects flying by, we built a third-person view football dodging game with Unity. We instructed the participants to control the avatar to dodge the footballs by moving left and right. After the football flies past the avatar, vibration motors on the corresponding side vibrate in sequence, from the front to the back. In this case, motion ring performs an asymmetric tactile motion. For both motion event types, we compare 3 haptic feedback conditions: motion ring, static vibration, and visual only. The motors that vibrate for the first 2 conditions are the same. The only difference is that for static vibration, they vibrate simultaneously instead of in sequence. As for visual only, no haptics are applied. The 3 conditions are counterbalanced by a Latin square. We recruited 12 participants to rate directionality, enjoyment, realism, and immersion using 7-point Likert scales, and rate the 3 haptic feedback conditions based on their preference. This plot shows the result of teleportation. We can see that motion ring has significantly higher scores on directionality and enjoyment when comparing to static vibration, and the scores significantly higher on all 4 aspects when comparing to visual only. Participants also comment that motion ring can well simulate the wind pressure in teleportation. This plot shows the result of the football dodging game. Motion ring has a significantly higher score on directionality when comparing to static vibration. Participants comment that motion ring did create the sensation of a football flying by. For preference, 92% and 75% of the participants choose motion ring as their top choice for teleportation and football dodging, respectively. We present motion ring, a vibrotactile headband that creates the sensation of 360-degree tactile motion around the head. We summarized a perceptual model for creating apparent tactile motion around the head that includes vibration duration, vibration intensity, and motor spacing. We proposed symmetric and asymmetric tactile motion patterns around the head for virtual experiences. User evaluation showed significant improvement in directionality and enjoyment, as well as being the most preferred by users. This is the end of my talk. Thank you for listening.